This lesson is on the gradient, tangent planes, and normal lines. Now, in an earlier lesson, we looked at tangent planes and normal lines just by focusing on the partial derivatives. But here we're going to add an extra tool that will make this a little clearer. So recall a big fact. The gradient is orthogonal to level curves. But what are level curves? They are of the form f of xy equals c for various constants. And we could think of it as a topographical map for a mountain. Here's what I mean by that. So here I have three level curves for a surface. Here are all the points where z equals 0 on the ground. Here's all the points where z equals 50. And then there's all the points where z equals 100. Now, if you're trying to get to the top of the hill, you're not going to walk this way. That's not getting you to the top of the hill. You want to walk orthogonal to the level curve. If you walk orthogonal to the level curve, that will get you up the hill fastest. Wherever you are, walking orthogonal to the level curve gets you up fastest because we know, again, the gradient is orthogonal to the level curve. That's going to be important for us to use. But we can also think about this in 3 dimensions, namely, so the gradient is also orthogonal to level surfaces. Now, I cannot typically graph f of x, y, z, but I can graph f of x, y, z equals a number. That moves it down to 3 dimensions. So if we know something is orthogonal, that will help us find the equation of the tangent plane because I need the normal vector to the tangent plane to find its equation. So here's our goal. We have z equals x squared plus y squared. And we want to find the equation of the tangent plane and normal line. Find the equation of the tangent plane and normal line to that surface at the point 1, 2. Now, do we know what z equals x squared plus y squared looks like? So here is that paraboloid. That's what it looks like. And we can find the point 1, 2, 5. That will be the point on the paraboloid. And we are interested in finding out where the tangent plane is at that point 1, 2, 5. So we see that blue dot there. What will the tangent plane be and what will the normal line be at that point to that surface? Now, what's our goal? I want to use the fact that the gradient is orthogonal to the level surface. Now, z equals x squared plus y squared is not a level surface, but I can get there. How can I get there? Let's rewrite this as 0 equals x squared plus y squared minus z. 0 is a constant. So I can think of this as some constant equals x squared plus y squared minus z. And then what can I conclude from that? What I conclude from that is x squared plus y squared minus z equals 0 is a level surface of what? Of big F of x, y, z equals x squared plus y squared minus z. And I want to emphasize the fact that you cannot graph big F of x, y, z. That would require 4 dimensions. But this graph I started with, that paraboloid, is a level surface of this 4-dimensional surface. And our big fact is that the gradient is orthogonal to that level surface. So having big F of x, y, z here, big F of x, y, z is x squared plus y squared minus z. What is the gradient of big F? With respect to x in the first slot, 2x. With respect to y in the second slot, 2y. With respect to z in the third slot, -1. Now, I was interested in this at the point 1, 2. So what is the gradient of f at the point 1, 2? What am I getting there? Recognize the z value there would be 5. Yes? You see that? 1 squared plus 2 squared is 5. So on the surface, that gradient will be at 1, 2, 5. What do we get there? 2 times 1 is 2. 2 times y is 4. And then the third slot is -1. So I argue this should be orthogonal to the surface at that point. So let's see if that's the case. So I have the curve up here, z equals x squared plus y squared, and I have the point 125 on that surface. We see it? And I'm putting in the vector 2, 4, negative 1. What is that going to look like at the point 125? And you'll notice it sure looks like it's orthogonal to the level surface, but that means it's also orthogonal to the tangent plane. So that will enable us to get the equation of the tangent plane. How? What are we going to need to use here? So coming back here, what do we know? The normal vector to the tangent plane will be that 2, 4, negative 1. And the point on the tangent plane will be 1, 2, 5. So that should be enough for me to get the equation of the tangent plane. If we have a normal vector and a point, relatively easy to find the equation of the plane. The normal vector components are going to give me the coefficients for my tangent plane. 2x plus 4y minus 1z will equal something. What is that something? How do I find that something? I plug 1 in for x, I plug 2 in for y, and I plug 5 in for z. And what does that give me? That equals 5. So that should be the equation of the tangent plane. So let's go take a look at the graph to see if that's the case. Going to the graph, I've put that in there, 2x plus 4y minus 1z equals 5. It seems to be going through that point. There is the normal vector. Does that look like that is the tangent plane? It looks pretty good to me. Looks like that's the tangent plane to the surface at that point. We also want to find the equation of the normal line. So how are we going to do that? We're going to have x equals, y equals, z equals. We're starting at the point 1, 2, 5. The change in x is 2, so it's 1 plus 2t. Change in y is 4, 2 plus 4t. Change in z is negative 1 minus 1t. If you prefer, we can write it as a vector valued function. R of t is 1 plus 2t, 2 plus 4t, 5 minus 1t. That should be the equation of the normal line. Let's see if it is. Let's pull up the graph. We see the normal line. We see it's extending out past the normal vector and going infinitely in both directions. That looks pretty good. So let's remind ourselves of the strategy we had to use here. We started with the surface z equals x squared plus y squared, rewrote that as 0 equals x squared plus y squared minus z. Recognizing 0 is a constant, this is from this family of curves, x squared plus y squared minus z equals c. And these are the level surfaces, actually. These were the level surfaces of f of x, y, z equals x squared plus y squared minus z. Those are the level surfaces that we're dealing with. And then what did we do? Then we took the gradient of big F, because that will be orthogonal to the level surface. But if it's orthogonal to the level surface, it's also orthogonal to the tangent plane. So the gradient of F is also orthogonal to the tangent plane. So in essence, the normal vector to the tangent plane was that gradient of F. Once I had the normal vector to the tangent plane and the point was what? Was 1, 2, 5. If I have the normal vector and the point, then it's relatively straightforward to solve for those two things, the tangent plane and the normal line. That is our process of how we use the gradient to determine the equation of a tangent plane and a normal line.